So again, we have a scalar field in 2D in exercise 9.2, number 2. This time I explicitly call it a curved surface, which is to say, to solve this exercise, it's even necessary to interpret this field as to be displayed as a curved surface concerning the z coordinate pointing towards us now in our current view, okay, or sometimes almost more often even pointing upward, okay, in the perspective view. Now, so I please carefully read. The following 2D function represents a curved surface in 3D, of course. So it's called a two-dimensional function simply because it has two independent variables, and the domain lives in the xy plane. So it lives in a two-dimensional vector space. And it's sort of, you could say, a question of taste, whether you visualize it using a third coordinate like z, or whether you don't, because z could also be something like a physical property, like, as I told you, temperature or charge density, things like that. So that's why it's not automatically a three-dimensional situation. Mathematically, first of all, it's two-dimensional. And we have the freedom to choose a third spatial coordinate to visualize the function value. That's the best way to understand why we're talking about 2D fields, although I'm using a three-dimensional representation now. Now, in this picture, let's try and find the equation of a certain tangential plane constructed through one of the surface points of this curved surface, which is given with all three coordinates theoretically, has to be -2 for x, -5 for y, and then, of course, the function outcome of -2, -5, which we still don't know at this moment, but it's the z value, right? So, and calculate also after finding the tangential plane equation, the increase in height, delta z, for delta x equals 1/2 and delta y equals 5/4. So that's just well, some sort of walking, you could say walking along the tangential plane. Because you see, in mathematics, every time we use delta symbols, we're not talking about something differential. So it should be clear from the context of this exercise that this is meant as an approximation referring concerning the real function, but it's not an approximation as long as we decide to stay on the tangential plane. You understand the difference? Because the tangential plane, of course, will always deviate from the true curved surface the farther away I go from my starting point. So it's quite an easy situation, if you once understood it. So I took the effort and gave you the two-dimensional domain very explicitly here, because I found out it's rather special. It's because in this case, when z equals, it should be z as a function of x and y, equals ln of x over y. Why is it so special? Well, first of all, we have the usual problem division by 0, which we should not or can't do. But then again, we have the natural logarithm, which has, as you all know, a domain of r positive. Means even the 0 is forbidden as an argument. So, but this is just a side note, but in the end, it means also x must be non-zero. It must be greater than 0. Oh, not really, because the other case is when y is negative but non-zero, and x also is negative non-zero, we have a fraction which gets positive. Well, like in the example -2, -5, we have -2 over -5, which is +2 over 5, and the function is well defined. So you understand what I mean? In the end, it means that either x and y must both be positive, or they must both be negative. That's all we allow for. You know the logical symbols, okay, for logical and, logical or, these two cases. So that's it's a little similar to here, just that the separation, well, it's different. Let's just not look at the graphical version. Okay. What do we do? Well, as always, we take partial derivatives. Now this time it's interesting to know ln. We all know that the natural logarithm has a derivative of 1 over its argument. So I do it using the same method as before. I'm taking the outer derivative without regarding any special variable, you know what I mean? It doesn't matter for which of the independent variables I differentiate as soon or as long as I'm concerned with the outer derivative, okay? So I take the outer derivative of ln of its argument, which is the reciprocal of its argument. What's the reciprocal of x over y? Of course, it's y over x. And then taking and multiplying the inner derivative, which is this time, remember, 1 over y counts as a constant factor, and x gets, well, differentiated for itself, so it gets to be 1. That's all. I get y over x, outer derivative, times 1 over y, inner derivative. Y cancels out. We know it's unequal to 0. I can cleanly cancel it out. It stays 1 over x. Quite simple. Now this brings me to an idea which is a little dangerous, but I just can't. I must tell you, okay? It's often the case that before you remember perhaps our very first session in this semester when we were doing the repetition on classical differential calculus, and I told you with logarithmic functions, it's always a good idea to use logarithmic rules in order to simplify the functional expression, which can afterwards be differentiated much more easily. And this is the case here also, and it's the explanation why the x derivative is so simple in the end. Well, the explanation is that ln of x over y is usually, I must say, the same as ln of x minus ln of y. And now we have a totally different view on this function. You see what I mean? Because this time, negative ln y counts as an additive constant, which goes away when differentiating over x. While the derivative of ln x, partial derivative, but it doesn't matter, for x is simply 1 over x. So that's why I get 1 over x in here. So, but this is not really quite correct, because, as I told you, it can be the case that x and y are both negative. And while the original function is well defined here, in this case, it's in this form, it will be not well defined. Because neither the ln of negative value for x is well defined, nor the ln of a negative value of y. You know what I mean? So that's the problem. We have restrictions for the application of logarithmic rules, and that's why we should be careful. But you can predict now, before I wipe it away, what will be the partial derivative over y. Over is saying over is easy for me because it's quicker than to say with respect to the tongue breaker. Okay, so you allow me now, because in that case, ln of x would disappear and negative ln of y would have the derivative negative 1 over y, and that's what it is. But anyway, wipe it out because it's not quite correct. So what's f index y? You remember this notation. I didn't even explain it. This is the modern notation for partial derivatives. We say f partial y in a very short form of x and y. Again, take the reciprocal of the argument, which is y over x. Multiply the inner derivative. This time I have, look here, sort of as before, but I think it was the other way around. This time I can rewrite this as to be x times y power negative 1, and I get derivative for y equals negative 1 times x, stays as a constant factor, times y power negative 2, which is then negative x over y squared. And I cancel out the x here and here, and also one of the y's. You see, the y in the denominator cancels against one of them, those in the denominator. Everything that remains is negative 1 over y, so it was not a surprise. So the gradient would be 1 over x, negative 1 over y, this time. And this time it really makes sense to use the gradient, although it's not asked either here, and neither in the first exercise nor in this one. Well, it's because we will see later. Well, it's not necessary, but it's possible to give the equation for the tangential plane to put it in a form which uses the gradient. I will not even do this, but let's just look at it and also insert our special point with x equals -2 and y equals -5. If I do so here, I have the reciprocal of -2, which is -1/2, and I have the reciprocal of -5 here, which is then +1/5. So that's it. And then next, we remember together what has been the general form, or what is the general form of the tangential plane at position x0, y, or let's say x null, y null. This is more often used in the wording. Let's call this the starting position, or also the touching point. It's not the point really, okay, because we still need the z component, but it's constructed at this position. So that's what you all know, and I just write it this simple way, z of x and y. Don't forget also the tangential plane, although it's a linear function, quite surely, of x and y, will be a function of x and y. Don't mix it up with the original function, which is non-linear, okay? So what do we use? We use this as a starting value for z, of course, we use the function value of x0, y0. Then we add, and now that's important, by using the partial derivative for x at position x0, y0, we use this as a sort of a slope factor to be regarded when multiplying, when moving away from our starting position in x direction. You know what this is? If imagine you wouldn't have, imagine this one, so imagine this is not there. So this sort of looks like the famous and well-known tangent equation, right? Of a simple function. The only difference is that you would have the m factor here, like the slope of the simple slope of the function, right? And so this is the two-dimensional version just of the tangent equation, nothing else, right? That's the best way to understand it, because simultaneously, while moving away from my starting position in x direction, simultaneously I can also walk away starting from y null in the y direction. So it's a combination of both. But regarding this contribution, I have a weighting factor of the partial derivative for x at the starting point, and here partial derivative for y. So that's quite convincing, at least, okay, what we get here. Now that's it. We just fill in, and z of x and y will then be, now you will know why I put ln2 minus ln of 5 here. Actually, it's the ln of -2 over -5, and I told you that my logarithm rule is not so easily applicable, but it is if I kill, let me allow to say kill, the minus signs. Okay, I cancel the minus signs. So since I have ln of -2 over -5 equals ln of 2 over 5, I can also say ln of 2 minus ln of 5. Not to forget, this is still negative. This is this is actually negative, but that's for a different reason. Has nothing to do with the minus signs of the arguments. It's because the ln of 2, you know, it's very famous. Simply speaking, 0.7, okay, is clearly a lower positive number than the ln of 5. So I get a negative difference here, but that doesn't matter for our purposes. So now look here. That's why I put the gradient. Well, I could also just look here. The x component of the gradient is fx of -2, -5. So I must use -1/2 at this here at this position, and so I have -1/2 times, and now I'm already here. I take my variable x minus the starting value of -2. So it's x minus -2, it's x plus 2. parenthesis closed, plus next contribution 1/5 for the fy value times y minus -5, so y plus 5. And now I want you to see that, firstly, this is clearly a linear function of x and y, since it's a planar equation, right? And also I want to show you, for your connection to your school, your knowledge from school, you can easily bring this in the form of a plane equation in parameter form, as you've learned long before knowing what is a function of more than one independent variable. Well, this is our constant starting value. Then I just remove the parentheses here. I get -1/2 x. Here it is. And I get, from behind, I get plus 1/5 times y. And then, but also -1/2 times 2, which is -1, put it here. And then plus 1/5 times 5, which is also this time plus 1. So these cancel out, but everything else remains nicely. Just look, if I pull, well, yes, all the terms containing any variable to the left side. So I leave this z to be here it is, okay? And then I pull 1/2 x to the left side with a positive sign, and 1/5 y times y with a negative sign, -1/5 times y. So then I have all my three coordinates here in a linear combination, and I leave the, I put the constant to the other side. Did I? Oh no, right, I leave them on the right-hand side. So where it is ln2 minus ln5, still negative, but the structure of this equation, quite clearly, this is a side note, it's not part of the exercise, really. The structure of this equation is a times x plus b times y plus c times z equals d. Very well known, the standard form of a plane equation in coordinate form, short KF for coordinate form. And even, as you know, you can read the normal vector from this equation. Well, you would usually, it's just the ABC vector that's normal to the plane. In case you wonder about my numbers here, I'm just preferring, I just prefer whole numbers. And that's why I don't, look, I could write down 1/2, -1/5, and then 1. But as you see, I can easily stretch this vector by a factor of 10 to get whole numbers. If I do so, I get 10/2, which is 5 here, -10/5, which is -2, and 10 for the z compound. Very nice to see. This is the normal vector to this tangential plane of our function. Well, this was a little journey for you to get familiar with these concepts, because we will be concerned with the three-dimensional case from now on, which is more interesting, of course, and more important.